So here we are again, back with Turing Complete. And we are going to continue our journey through the campaign. The next level that we are going to play is the conditions level, because everything else is going to be much easier and way more fluent when we move up the tree once we've completed this level. So this level has a value input and 3 condition bit inputs. The 3-bit select the condition as shown below checks the value against the selected condition and outputs green if it is satisfied and red otherwise. We're going to leave this open because we're going to have to see how we're going to use these conditions. Oh, this level is not going to be so easy, but we're going to make it. So, is there a way to check for equality? This should be usable. Oh, this is a tiny box. Wait a second. There has to be a way to calculations program. No. I mean, we could use the component factory, right? And within the component factory, we could build components that would allow us to do these comparisons. But for now, let's try it without. I know that in the past we're just going to never mind. We're just going to check 1 bit. We are not comparing 2. This is going to come later. Okay, so you're the instruction bit, right? So first of all, what we are going to do is, we're going to do it this way, I guess. We're going to decode this because we have to, right? Not like this. This is never. So when you are green, we're just not gonna do anything, I guess. Yes, equal to 0. We could like, if this is true and none of the, how many do we have to do? 1, 2, 3, 4, 5, 6, 7, 8. 2, 3. How unfortunate. We will have to take this, rotate it, and do it this way, but this is going to be fine as well. So here we are. So now how do we do it? If the value is This is going to be easier. If the value is below 0, this would be if this one is true. We know that it is below 0. We could use switches. Switches are good. This is going to solve it. So here's the next one. Which is the opposite, right? If it is greater than 0. Now this would be greater equal. Which one is this? No. One that comes before the last one. A little bit dirty, but okay. Here we are. Doing this. And this should do the trick, right? So if you are a negative number, which is, oh, here it is. And we're checking for a value below 0, you're true. And you're not true in case of 0, right? Alright, so now we are going to check for value above 0. Or above equal 0. This is our condition, right? Yes. So we're above 0. We're at 0. Negative. It works. Perfect. Okay. Okay, so if none of our inputs is true, which we can check by chaining some ors together, that would mean that we would have a 0. Wait a second. You are the one. You're supposed to check if it is 0. Here we go. So I guess the opposite would be unequal to 0, right? And then we would have to AND for the others. So if any of these is true, if any one of these is glowing, that would mean that it is not 0, which is this case. Alright. We have it. Oh, this is messy. Sorry for that. So now we'd have to use OR gates, right? We have a value above 0, which is this case, right? No, it is not. It is this case then. Or is it this one? I guess it is this one, yes. Yes, it is this one. This equals 2. Sometimes I get confused. This is the way that we read it. Right to left, top to bottom. Maybe I can keep this in mind. So if it is bigger than 0, why isn't it working? Oh, this is below 0. So if it is below 0, let's go with this. Makes more sense. If it is below 0, which is this condition, or if it is equal to 0, which is the first condition, which is this one. Yeah, if any of these lamps goes on, then we have the case that it is either below 0 or equal to 0. So you are smaller equal. So the next condition is always you go straight into this. Apparently you don't. Apparently you will have to be done this way. I mean, since we're doing this, we might as well go with this one for the always off, just for the purpose. And I should have probably color coded it, which I think I did in my previous playthrough. Yeah, just for the sake of cleanliness, we're gonna do it like this. Okay, when is it strictly greater than 0? So if it is not 0, right? In which case is it 0? In this case it is 0. If none of our lamps is on, it is 0. This condition. Or we're gonna go with or, because we're gonna need or. Wait, it is and. It is and. Sorry. So it is below 0, right? No, it is not 0. And it is smaller equal to 0. Which one is that? The one before the last. This is this condition. So that would be this one. And I guess now we'll add a switch, because I'm afraid of a short circuit. Let's just do it like this. Let's just do it like this. So this should solve the level, right? And it does. Congratulations, your component has been saved to the component factory. Great. It is messy. It is messy as all hell. Maybe I'm gonna rebuild it. But for now, since I know that later we will unlock components that will let us do comparisons straight in one component, we are going to be able to build it way cleaner. And this is why we are not going to do it for now. Level completed. Instruction decoder. This is the level that we're going to play now. The circuit is built. The circuit you built in the registers level can copy values between registers, while the arithmetic engine can do different operations on two inputs. But you need to be able to do both in the same circuit. To do this, build a decoder which will decide which mode our computer is in, based on the 2 bits we haven't used yet. Okay. Does that make sense to you? We have, at the registers level, we have, we have split the instruction byte, and we have used 2 decoders, right? This 3 defined the destination, while these 3 defined the source. So the remaining 2 would be used to decode an instruction. And this is what we are going to do now. The first one is immediate. The next is calculate, copy, and condition. It means any value. Yeah, of course. Now, to distinguish between the instructions of 4 different kinds, the 2 highest bits will be used to determine which mode we are in, as follows: immediate, calculate, copy, and condition. Yeah, here this means any value. Determine the mode we're in from the input. Send green to this corresponding output. Yeah, this one is just luckily we can just use a decoder. And this should do the trick. Yes, it does. Your circuit has been saved to the component factory. Great. So this level is has been quite easy. Calculations. Time to merge the arithmetic engine circuit you've made previously with the register circuit. The calculation circuit was saved in the component factory and can now be added as a component. If you forgot which pin does what, check the circuit in the component factory. Use the decoder you've built to figure out if we should copy between registers or do calculations. Here are 4 different modes: immediate, calculate, copy, condition. For this level, you only have to worry about the copy and calculate mode. Check the instructions by clicking on the instructions icon in the top panel for the details. When in calculate mode, take register 1, register 2 as inputs and save them into register 3. Don't forget the 3-bit decoder component as a disable bit. Alright, for this level you only have to worry about the copy and calculate mode. Check the instructions by clicking this icon. Yeah, of course, okay. For this level, an extra pin has been added to the registers. This pin will always emit the value of the registers regardless if load is selected or not. Oh, right, okay. Great. So, to calculate, we would use our ALU, our algorithmic logic unit. And we would take, this is register 0, right? We would take register 1 and register 2, do our calculation, and save it into register 3. Which, I don't know, I guess it doesn't matter where exactly we are. I'm gonna make this clean. So we're going to be using this machine for a while. So here we are. And it is going to take our instruction byte as well. So here we are. And we're going to use a switch. This switch will be used to determine whether we are going to feed our this is unfortunate. Whether we are going to feed our logic unit result into the circuit, and we're going to move this a little bit to the left because this is why the level told us that the decoders have a disable bit. Because we would, when we're in calculate mode, have to disable the destination and the source as well, I guess. And rather take the values from 1 and 2, feed them into the ALU, activate our register, and we should color code this. This is going to be, let's say, important. Yes. So once we're in calculate mode, we disable the destination and source. And maybe we could actually do it like this. If it is not in copy mode, we disable them. This is going to be handy later. So we're going to have to use a color. We're going to use orange for the calculations. Which means that we're going to use it everywhere in the calculations tree. We're going to have to keep that in mind. Oh, interesting. Why doesn't it work? Oh, because I connected it accidentally to the bus. So this does calculations. And in case we're not in copy mode, the destination and the source are disabled. And this should do the trick. Copy mode. What color do we use for copy? Maybe we just use white. Yeah, let's go with white. Here we go. Oh, it doesn't work. Why is that? Oh, I guess. Copier. This is copier. So now it's working, right? No, it is not. Register 3 should have the value of 255. Okay, we are in calculation mode. What is it? Oh, because we need an OR and not an AND. Now it is working. Here we are, level completed. Great. Calculations. We've locked the manual entry instructions. Calculations. Type miscellaneous. Miscellaneous? I'm not sure. Okay. Program. This is going to be interesting. What is this about? Oh, the instruction. Yes, yes, yes. The program. The instruction input component has been removed. It has been replaced by a program component. Every tick uses the counter to load the next instruction from the program's memory. You must use the counter component you unlocked earlier for this level. Yes. Can we move this? Yes, we can. Great. So, how did you... Wait. Alright, interesting. Oh no. The counter. Alright. No, the counter's gonna be green. Here we are. Let's see, does this work? Yes. That's basically all there was to it. Later it's going to be of importance. Because in this level... No, here we're going to immediate values. In the next level, the Turing complete machine. I'm gonna talk about this later. In the Turing complete machine, I'm just going to tell it to you now. In the Turing complete machine, we are going to override the value of the counter by a value, I guess the value that is in register 0, and so we determine if we are going to override the value in the counter depending on a condition that is met or not. We need a way to directly move numbers from our program into our registers. For this we use the immediate mode. When the highest 2 bits are red, which are these two, we are in immediate mode. When in immediate mode, the whole byte is interpreted as a number that we save into register 0. This means we can save any value between 0 and 63. Right, here we are. Any value between 0 and 63. This is register 0, right? And this is immediate mode. What color do we use for immediate? Maybe black. Or maybe turquoise. We haven't used turquoise so far. We have though, so we are going to go with dark blue. We haven't used dark blue. Let's go with dark blue. No, I dislike this color. Black is great. Also, I don't know how it corresponds with this. So here, once again, no, we are going to load in this case, right? No, we're going to save. So we're going to have to use an OR again. Going to save into register 0. And we're also going to feed our bit directly into the bus, but only if we're in immediate mode. Let's go. Here we are. Immediate values, miscellaneous. Let's go. Another entry. Now we are going to complete the computer. Until this point, all possible programs have been confined to running in order, byte by byte. Before only code could influence memory, now memory must influence code. With the addition of conditional logic, our computer can run any algorithm and calculate anything calculatable. Which is cool, isn't it? And I guess it's a little bit far-fetched because it's going to take immense amounts of ticks for complex calculations, but in theory it could. Before only code could influence memory, now memory must influence code. With the addition of conditional logic, our computer can run any algorithm and calculate anything calculatable. Yeah, once more. Here we have it. The final thing we need to add is a mechanism for changing the program's counter through instructions when certain conditions are met. When the two largest bits are green, we are in condition mode. In condition mode, the value in register 3 is compared against the condition defined by the 3 lowest bits in the instruction. Alright. The 3 lowest bits in the instruction. Yeah, well, this is the instruction, right? If the instruction, no, wait, the value in register 3 is compared against the condition defined by the 3 lowest bits in the instruction. If the condition is true, we override the counter to the value in reg 0. Yeah, alright, okay, got it. Additionally, changing the counter means we can skip instructions on conditions or have instructions run in a loop. Yeah, the conditions, that makes sense, right? Wait, why is it only the 3 lowest bits in the instruction? Oh, of course. The 3 lowest, not the 3 highest. Yes, of course. I was thinking for a second that the way our condition was built is wrong, but this is not the case. I just made a mistake in my thinking. Here we are. First of all, the instruction, right? We are going to use green. We said we are going to use green for this one. Green. So, which registers of relevance? Register 3, right? So we're going to move this down to register 3, and we're actually going to move it below. Just so. Unfortunately, this is not the cleanest variant, but hey, this is gonna be all right. So here we have our condition. And if the condition is true, we are going to override the value in the counter. This one's unclean as well. We're going to override the value in the counter with the value in register 0, right? Here we go. But since this is just going to check for the condition every time that a tick comes in, and send a value according to the value that is saved, send a signal according to the value that is saved in register 3. We're going to have to use a switch so that we would be able to stop the counter from overriding every time that the condition would be met, which is in many cases just a random number. I hope this made sense. I'm sorry, it was a little bit stuttery, I guess. Yes, you did it. I thought you were just the odd-looking hairless ape creature, but actually, but you actually built a real computer. Amazing. Great. Level completed. Program. Oh, programmable memory component. Great. And Turing complete. Manual entry. Maybe we can actually have a look at this. Certain computers, like simple calculators, are limited in the algorithms they can perform. They cannot perform any calculation that requires looping or recursing or arbitrary amount of times, Technically, machines without looping or recursion can only deal with a combination with combinational logic. Turing-complete machines, on the other hand, are as powerful as it is possible to be. A Turing-complete machine may have a slow CPU, but it is powerful in the sense that there is no computable algorithm it can't perform. That's crazy, right? Really crazy. Yeah, I guess. I don't know. Since we only have a few registers. Certain algorithms. I don't know if you have if you can imagine this. Certain algorithms are gonna take forever and gonna be infinitely complex, especially when we are trying to compute some more complex things or ideas. But yeah, well, in theory it is possible. So here we are. We have our first Turing complete machine built, and this is where we're going to end this video. I hope you had fun, and in the next video I'm going to show you a few of these levels. Let's see how far we get. Goodbye.